All right, yesterday we finished up talking about hydrogenation or reduction of alkynes, and we said that it's really similar to the reactions we saw with alkenes, where you can use hydrogen gas along with a metal like palladium or platinum and go straight to the alkane. But we said that if we want to stop at the alkene, we've got to use more clever methodology. If we want to go to the cis alkene, we always need to use Lindlar's catalyst in H2 or the P2 catalyst, one of the poisoned ones. And the reason it only adds cis is because it actually takes place at the surface of the metal, which means it only delivers hydrogen to the same phase. The dissolving metal reduction, the one on the bottom, doesn't go through surface chemistry. It actually goes through a radical anion intermediate, and because of that, it favors the trans alkene. It looks really similar to the alkene reactions. I would try to really remember which one gives you cis and trans, because this becomes a valuable synthetic tool. All right, so let's continue on to a new reaction. Hydrohalogenation. Sounds familiar, right? We just covered this with alkenes. So let's review what we covered with alkenes. If we add HBr to an alkene, will this be Markovnikov or anti-Markovnikov?
So pretty much we're going to go through the same thing but with alkynes?
Exactly. It looks very similar. It'll be Markovnikov. Markovnikov is the more substituted side. So in this case, we would add bromine across here. So let's make an alkyne hypothesis, if I can talk. I want you guys to help me with this. We're going to use a terminal alkyne. We're going to react it with HBr. Which side of the alkene is going to react? Do you think it's going to react with the green side or the blue side?
Blue side.
Where's the bromine going to end up? On the green or blue carbon? Green carbon. So our gut instinct for these reactions would be to do something similar to what we saw last chapter, where this pi bond could grab a proton, kick off our bromine, give us our proton off of the end and form a carbocation there. And we would hypothesize that this bromine would then add into the carbocation in the Markovnikov position. However, there's a problem. This is called a vinylic carbocation. And experimental evidence says that this is not observed. Because chemistry is never easy. The other thing chemists like to do when they run into a mechanism that doesn't fit with their standard model is they actually like to do experiments to try to deduce what the mechanism is. And the easiest experiment that they ran with this was a rate experiment. And they found out that this is a third order reaction. And specifically, they found the rate equation, and they found that it's equal to the concentration of the alkyne times the concentration of hydrobromic acid squared. So what the heck does this mean? Yeah, remember that a rate equation is describing the collision of the different components. So if you think about this, this doesn't just go through the collision of an alkyne and one equivalent of HBr. It actually requires two equivalents of HBr to proceed. So let's take a look at the new hypothesis that was formulated after this. The new hypothesis that came out of this study said that, okay, we've got this carbon-carbon triple bond and this hydrogen. This time we're going to have one equivalent of our HBr up here. We're going to have another equivalent of our HBr down here, and it's going to actually go through a termolecular transition state. Oh, sorry, this should be BR. Okay, I got that. And then this pi bond is going to jump up, grab this, and then kick off our bromine. It looks kind of crazy, so let's draw the transition state. When we do this, we're breaking the bond between HBr. We still have a sigma and a pi bond between these two carbons, but we're breaking one of these pi bonds. We've got this hydrogen out here, and we've got the CH3 over here, and then we're forming a new bond to a proton up here, and we're breaking a bond with the bromine. This is one of the more exotic looking transition states for an elementary organic reaction. But it gives us the same product that we predicted. Oops. Let me change this. Here we go. Yep, it gives us the same product, but the mechanism isn't quite what we would have hypothesized. So, yeah, try to. It's one of those things where it's a subtle detail, but it's an important one, because if you're running this reaction, you actually need two equivalents of your acid in order for it to proceed, not just one. Yep?
We observed last section that the double bonds were negative charged, but what is causing the induced dipole or whatever to next to bromine attack the triple bond instead of the triple bond attack first, like double bond?
That's a good question, and it gets into the instability of that vanillic carbocation. That's so improbable that the instant that top carbon or the carbon on the right starts to grab that proton, that bromine instantly gets attracted to that other carbon. So it happens all at once and concerted. Yeah. And like I said, this is a termolecular transition state. Yep.
In the first picture there, should there be an arrow going from the double bond on the bottom HBr to like the hydrogen, or where do those electrons come from?
Essentially, it reforms HBr again. So the electrons from that pi bond go over to that carbon, so you get a proton, so H plus and Br minus around in solution, and that would be your byproduct.
Right.
So you get new HBr floating around. Yep.
So does this only work with terminal alkene?
It will work with any sort of alkene, but the regiochemistry is always going to be Markovnikov for a terminal alkene. Does that make sense? So just like we predicted up here, we predicted that it will be Markovnikov. If you've got an internal alkyne, you don't really have a Markovnikov side. So that's why I showed this example. Yeah. Yep.
What does termolecular transition state?
Termolecular just means it's the collision of three molecules at that transition state. All right, so let's take an example. And the example I have is one that's pretty similar, and I'll show you guys a simple step for reversing it too. So let's start with this example. We've got phenylacetylene. Do you want me to scroll down or up? Like this? All right. And we're going to add HBr in excess.
Is that if fancy of saying HBr?
Yeah, or even more than that. It could be 4 or 5. It could be 1,000,000 equivalents of HBr for all we care. We're adding it in excess. What will our product be? So let's ask ourselves, is the bromine going to add on to the red carbon or the green carbon? Red carbon. Okay, so we could theoretically get this to stop, and we could get a bromine to occur or add onto the red carbon. But if we've got excess bromine, are we going to stop here? No. Where will our next bromine add? Will it add to the red carbon or the green carbon?
Green carbon.
Oh, this goes back to last chapter's chemistry. Which is the Markovnikov side? The red side, right? So again, it's going to add to the more substituted carbon.
So if it wasn't excess, then we'll stop at that point.
Yeah, it would stop there if we didn't have excess. So this one's probably not going to be easily isolated in excess conditions because we're going to overshoot it and we're going to brominate twice. Chemistry is not easy, but it's fun. And this is called, again, a geminal dihalide. And a challenge for you guys to see if you were paying attention the other day. What if I want to go back to my starting material? Let's think about this. We've got a haloalkane. We've got a good leaving group on there. What sort of reaction could get us back to the double bond? Yeah, an elimination reaction, and then we could push it one step further all the way back to the alkyne. Just like we saw in the problem of the day first term, and we covered again yesterday, a common base that we use is NaNH2. Oftentimes we use this in excess, just like with the bromine. However, if we add too much, we run the risk of deprotonating that alkyne. So there's a simple solution to this. What if we want that alkyne to have that terminal proton? What could we do as a second step? Yeah, add in water or a really weak acid. So oftentimes there's a second step to this reaction where we add water. That way we end up with that terminal proton back on our alkyne. So now we can go from an alkyne to a haloalkane and back again. It's a pretty useful trick in synthetic problems. All right.
Can you explain again why we need to add water?
So if we don't add water, this proton up here would be deprotonated, right? Because if we add excess base that's really, really strong, it's going to rip off that terminal proton. So we need to reprotonate it as that last step.
But if we do the first step, it's already deprotonated.
If you do exactly 2 equivalents of sodium amide, you could theoretically get straight to your product. However, most of the time it's just easier to overshoot it and add water in when you're done.
Okay, so kind of like we deprotonate it, but we add water to let it back to the product.
Exactly. Yeah, we add water in to reprotonate our terminal alkyne.
If you use that base, wouldn't it produce the Zysa product? And don't we want to make it the Hoffman product to get back to that exact alkyne?
In this case, is there a Zaitsev or Hoffman difference? We only have one set of beta protons. So we only have one potential alkyne product. So we can't say that we're going to get Zaitsev or Hoffman here. Yeah. All right.
We have an anticoplanar in the ring structure.
Yep, remember that methyl group can spin around, so any of those protons coming off of this methyl group can be anticoplanar.
But will they make the Zysa from that?
In this case, there's no Zaitsev or Hoffman differentiation because you can only get one alkene out. There's no beta protons over on that carbon. Sorry, that was a bad arrow.
No?
So now the question is, how could we get anti-Markovnikov addition? Peroxide, there we go. All right, so let's cover this. Anti-Markovnikov addition. It's pretty straightforward. We said with alkenes, we could get anti-Markovnikov by treating this with HBr and peroxides. And it would always add to this anti-Markovnikov carbon on the less substituted side of the alkene. The same thing is true with alkynes. If you take phenylacetylene and you treat this with HBr and peroxides, you're going to end up with a mixture of products. What do you think that mixture might be?
Maybe in the first step it has to be that double thing, so it's going to add Markovnikov, and then the second step it would take effect in the process.
So we would predict it's going to add Markovnikov. So let's think about this. We could have, I'll draw one potential product out and hopefully it'll become clear. So we could add, oops, sorry, this should be a BR. You could have it like that. What do you notice about this alkene? It's trans. So we will probably end up with a mixture of cis and trans alkenes out of this, where you could have one bromine pointed up, the other one pointed down, and get two different products. Let's keep this the same color.
So on the alkenes, they usually make serocenter, but when it comes to alkynes, you have to watch it for cis and trans.
Yeah, exactly. So if we were comparing these, are these enantiomers now?
Cis and trans.
Well, they're cis or trans, but how do we refer to them in terms of stereoisomers? Diastereomers, right? So these are no longer enantiomers. Now we've got a mixture of diastereomers that we have to worry about. Again, this goes through a radical mechanism, and we're going to cover that mechanism in chapter 11 in more detail. What do you think happens if we do this in excess? Yeah, you would again do another anti-Markovnikov addition reaction. Do you have a question, Sarah?
No, that's what.
Okay. All right. Now we're going to change gears a little bit. We're going to talk about hydration reactions.
Yeah, we can't read the back process.
Sorry. All right. You guys get it all?
Yes.
All right. Hydration reactions are pretty similar to alkynes again. So let's recall what we did last chapter. If I've got an alkene and I take acid and water, where is my alcohol going to end up? Is it going to end up on the blue carbon or the red carbon? There's a lot of mumbling. Say it with authority. Oh, come on. Blue. All right. Here's the addition product. It's going to do Markovnikov addition. What if we wanted it to do anti-Markovnikov addition? What reagents would we use? So it involves peroxide, but what's the first step? Yeah, the THF borane complex, so BH3.THF. That borane is essential towards getting the anti-Markovnikov product. Otherwise, if we're just using acid and water, we're always going to get the Markovnikov addition product. So let's look at alkynes. So let's say we've got a simple alkyne. And we try the same thing. We'll try acid and water. We get no reaction. We would predict that it should add to that blue carbon, right? However, when we run this, we can crank up the heat, we can crank up the heat, we can crank up the heat, nothing happens. The activation energy is too large. It's a little bit unclear to me why it is so large, but what's the trick when we have an activation energy that's too high? Catalyst, exactly. So here's what we're going to do. We're going to use the same starting material. And oftentimes chemists go through and they screen hundreds or thousands of catalysts in order to find one that works well. The one that works well for this reaction is mercury sulfate. All right. If we add mercury sulfate, we now can add the alcohol to the Markovnikov position shown in blue there. We're not going to go into the mechanism behind this because it goes through a bunch of organometallic chemistry. Yep.
Do we need to number those?
No, this is all one pot. Mix it and forget. All right, if we do this, now we've got a new alkene. And this is a very, very peculiar alkene. It's called an enol. Why do you think it's called an enol? Because it's got an alcohol, so that is where the all part of the enol comes in. Why do you think we start with the ene? Because it's an alkene. That's the easiest way to remember an enol, is it's an alkene alcohol, right? So it's an enol. Next. Yeah, as long as the alcohol is coming directly off of the alkene, it's considered an enol. And we're going to see this a lot more in third term, I believe, but this is our introduction to enol chemistry. All right, we still have this acid around. And we've got this alkene. So what do you think might happen? Give you a hint. Really similar to last chapter.
Where's the double bond?
Yeah, just like we saw last chapter, we could have this double bond attack our acid, get protonated, and when we do this, the proton that was added in is going to go to the less substituted side. And I'm going to draw in lone pairs now, and we end up with this carbocation. Yep.
Does that have to be under cold conditions so it doesn't favor protonation of the alcohol? Or
it could protonate the alcohol too. That's going to occur in equilibrium. But why is this such an unusually stable carbocation? Resonance, right? When in doubt, resonance. This lone pair can dump down and stabilize that carbocation. And we've got a positive charge that's delocalized up to that oxygen. So while we can protonate the alcohol, the carbocation is unusually stable for this situation. So this is a major pathway. Now if we still have water around, this water can act as a weak base and just pull this proton off and give us a new functional group. What's this new functional group called? It's a ketone, specifically acetone. This is called a keto-enol tautomerization. Yes, exactly. So oftentimes when you form an enol, it goes through a keto-enol tautomerization where you end up with the ketone, or occasionally you end up with the aldehyde. This is a really important mechanism, and it favors the ketone.
Professor, will we have product from the right one?
No, it exclusively goes towards the ketone side. You don't end up with the hydrate. We're going to cover hydrate reactions later on, but this particular hydrate would be really unstable, so the mechanism I have shown is the predominant one.
Is that two A's or one is the A, one is something?
Over here?
Yeah.
So that's tautomerization, I believe. Don't get angry if I spell things wrong, please. Equilibrium, in this case, always favors the ketone. What does it mean when I say tautomerization? Does anybody know what that word means? It's different than resonance. Resonance says that it's delocalization of electrons. Tautomerization means it's the same molecule, but with a proton that's been moved to a different location. So all we did in this case was in the enol, we added in a proton. And then down here, we removed a proton. So we didn't change the molecular formula at all. All we did was shuttle protons around to get a new product. So tautomerization is just code for moving protons around. All right, so now I'm going to give you guys an example problem, and I want you guys to help me out with it.
Professor?
Yep.
So does that mean like a hydride shift is a tautomerization?
That's not really movement of a proton, that's movement of a hydride. Okay. And so people don't refer to it as tautomerization. Yeah. Sorry, that was getting, yeah, that's a good philosophical OChem question. All right, so we've got this starting material. We want to do Markovnikov hydration. So I'm going to add in H2SO4 as our acid. And this is going to be in solution with water. And what was our catalyst that we need? Yep, mercury sulfate.
How do they find out those catalysts that fit for this reaction?
Oftentimes they screen hundreds of them. So they test it. Did it work? Nope. Move on to a new one. Did it work? Nope. Move on to a new one. Honestly, that's how they did this in the early 1900s. All right, so
now?
What's that?
What about now?
Now we've got a better grasp on it, and oftentimes we use computational methods, or we just rely on previous reactions that are similar to anticipate what catalyst might work in a new situation. All right, so let's predict the enol that would result from this. Again, we don't have to do the mechanism going to the enol. So we've got this blue carbon, we've got this red carbon. Where's the alcohol going to add on to? Red carbon. Okay, so now we've got a new alkene with our alcohol coming off of it. And let's just draw in these two protons coming off of the alkene. All right, now I want you guys to work on the tautomerization step, and I want you to check with the neighbor to see if you've got the tautomerization step down. So I'll give you guys a minute to work on the tautomerization, and then we'll reconvene. Yep. Not for this first step, but I do want you to show the mechanism for tautomerization. Man. I can't move that, so. If you think you've got the whole tautomerization, raise your hand just to let me know. All right. All right, a few people have gotten it. I'll get us started on this. So remember, the alkene is going to grab a proton. We're going to protonate the less substituted side. And we're going to get the carbocation coming off of that central carbon. And we said before that this is really stable because the lone pair from the oxygen can dump its electron density down. And CH3, so we've got these resonance structures. And then what's the last step? Yeah, water deprotonates the proton here, and we end up with our ketone. All right, so the problem of the day I gave you guys is directly related to the keto-enol tautomerization, so hopefully it's fairly intuitive. Double check your notes if you get stuck on it, though. All right, I'll see some of you in lab and the rest of you tomorrow.